Okay, sweet. So we have polynomial functions and rational functions today. So for polynomial functions, the notes is only this page. So nothing too crazy on these. So for the given four graphs, we're going to want to know how many real roots are shown in the graph. What is the minimum possible degree of the polynomial if it has only real roots shown? And write a possible equation for the function in factored form with the minimum degree. Okay, so to put that all in English for you, we're going to look at the x-intercepts of the graph, and x-intercepts are also called roots. So let me put that on there. So for a root of a graph is also known as an x-intercept. Okay, so we'll be looking at the x-intercepts of the given graph, and then from the x-intercepts, we are going to work backwards and create a polynomial function. So when I say work backwards, let me show you the process that we're actually used to. So remember that, let's say I have a function, f of x equals x plus 1 times x minus 1 times x plus 2. And if you wanted to find the x-intercepts, you would let f of x or y equal to 0. So that means you would take all of these factors, x plus 1, x minus 1 times x plus 2 equal to 0. You would set all of these equal to 0, all of these factors equal to 0, and you would get x equals -1, x equals 1, x equals -2. So that's finding an x-intercept. That's something we're used to. Now, like I said, for these notes, we're going to start with these x-intercepts, and we are going to work backwards. We're going to put them into factored form and then put them as a function. So we will be reversing that process. We will be building a polynomial from the x-intercepts. Okay, so stating that, let's look at number 1. Okay, so let me put all our values here. Here's 0. So to answer A for number 1, it says how many real roots are shown, or how many x-intercepts are shown on the graph. So how many x-intercepts do you guys see?
3.
3. Good. 1, 2, 3. So to answer A, we're going to say 3 roots or x-intercepts. Same thing, right? Okay. Now B says, what is the minimum possible degree of the polynomial if it has only the real roots shown? Okay. So here's something you may not have. Here's something new you may have never seen, or maybe this is something you've seen a long time ago. So when you're asking for the degree of a polynomial based on the roots, well, you have to look at your x-intercepts and see what the graph is doing. So at 0, we see that the graph is crossing through 0. And at 2, you see the graph crosses at 2. But when it gets to 1, what does the graph look like it's doing at that x-intercept of 1? Is it crossing or is it bouncing off?
Bouncing.
It's bouncing, right?
Bouncing off.
Good. It's bouncing off. So at the x-intercept of 0, we cross. At the x-intercept of 2, we cross. And at the x-intercept of 1, we bounce, or you can even say touch. So I'm going to really quick touch on this. This is something called multiplicities of x-intercepts or roots, however you want to say it. Okay. And if the graph at an x-intercept touches or bounces, so we can say let's say if graph bounces, then this x-intercept is said to have an even multiplicity. So if graph bounces at x-intercept, we have an even multiplicity. Now, multiplicity deals with the degree. So, hang on. Okay, so multiplicity deals with the degree. So if you have even multiplicity, what is the smallest even number?
2.
2. So this means that the smallest degree, the smallest exponent, the smallest power that this x-intercept could have is a degree of 2. So for an even multiplicity, we have degree of 2. Okay, and now if the graph crosses, so if the graph crosses at your x-intercept, you are considered to have odd multiplicity. And what is the smallest odd number?
1.
1. So if you cross at an x-intercept, you will have a degree of 1. Okay. So even multiplicity, we can say that we have a degree of 2. Odd multiplicity, we say we have a degree of 1. Okay. Now we can come back to answer B. It says, what is the minimum possible degree of the polynomial if it has only the real root shown? So for B, if I cross here, that is 1. If I bounce here, that is 2. And if I cross there, that is 1. Add these up, and what is the minimum degree that this graph could have? So basically, what is 1 plus 2
3?
plus 1?
4.
4.
Right? 4 is our minimum degree. And the reason we say minimum is because the answers for this could be many. And we're just trying to keep a minimum answer. We want the minimum answer for this.
So do you mean like the polynomial, like it would be like x to the 4th power? Is that what you mean?
Very good. Yes.
Gotcha.
So
Okay.
if we were to create a polynomial out of this, which we're going to do, the minimum degree of that polynomial would be 4. Okay.
So if okay, you said that if the graph bounces, then it's going to be an even.
Exactly.
So what we do, we do count the bounce in the graph then, right?
Yes, correct.
Okay.
Good. Very good question. All right. Cool. All right. So now we know roots. Now we know multiplicities. Now we know the minimum degree. Now we want to put an equation together. We want to put together an equation from these x-intercepts and knowing the minimum degree. So looking at our x-intercepts again, which we're at, sorry, I wrote all over this, which was at x equals 0, x equals 1, and x equals 2. Now, how could I reverse the x-intercept process to get my polynomial? And again, reference what we did in the beginning. Here's where we start, and now we work backwards into a factored form. So
we FOIL?
Not FOIL. FOIL would be expanding everything. All we want to do is take our x-intercepts and put them back into a factored format, or I can even say a linear format. So if I have x equals 0, then my polynomial will just start with x. If I have x equals 1, my polynomial will have x minus 1. And if I start with x equals 2, my polynomial will also contain a factor of x minus 2. Now think about it. If I set this equal to 0 and solve for x, what values would I get?
X
So you-
equals 0, X equals 1, and X equals 2.
Exactly. And those are the x-intercepts of this graph, right? That's it. That's all we have to do. So now we have put it in the correct form, and I don't think your homework makes you FOIL it out. It just wants you to create a polynomial for it. So C says, write a possible equation for the function in factored form with the minimum degree. So all we have to do left is put this as a function. We'll say f of x equals, but remember that the minimum degree should be 4. So at x equals 1, since it bounced, on our factor of x minus 1, it's going to get the power of 2. And the way to check your work here is if you put an exponent on all your factored terms, you have 1 plus 2 plus 1. That gives me my minimum degree of what?
4.
4. There you go. And that's it, guys. That's all we have to do there. Let me make this look pretty, though. Hang on. That looks sloppy. So f of x equals x times x minus 1 times x minus 2. And that's all it wants. Any questions on that? We good with that?
So what happened to your exponents?
Oh, see, good call. I erased it, right? I tried to make it pretty and I forgot it. There you go. See, there you go.
Ah,
I have a question.
Yes, what's up?
So would our polynomial literally be like the equation that you wrote? Like that would be our like polynomial that we found for it?
That's the form it wants it in because C says put it in a factored form.
Gotcha. Okay.
But if you wanted to FOIL everything out, you would get that power of x to the 4th.
Gotcha. Okay.
But
Okay. Cool.
our goal is only to put it in factored form.
Okay. Cool.
Cool. All right. Well, let's try it again. So we'll do number 2. Same exact thing. How many roots or x-intercepts do you see?
4.
4. Good. We'll just say 4 roots. And what is the behavior of the graph doing? Is it crossing at all of them? Is it bouncing anywhere? What do you guys see?
Well, kind of bounce, but
Is that at
It
1 it
bounces at
crosses,
1 and 4.
2 it crosses, 3
2
it
and 3?
crosses, 4
well,
it crosses.
bounces.
It crosses on all of them.
Okay,
That is a cross on all of them.
so they consider that little hump across.
Exactly. So even though it did this, yes, the last graph had that little hump too, but that bounced. So when I say cross, I mean cross the x-axis.
Okay.
So on all of these, we cross, 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 cross. So if we cross on all of those, that means they all have odd multiplicities. So that'd be 1, that'd be 1, that'd be 1, that'd be 1. And what minimum degree would we have?
4.
4. That is our minimum degree. Good. Okay, now let's create the polynomial. So C, look at our x-intercepts. You have x equals 1, x equals 2, x equals 3, and x equals 4. Now put these back into factored form. And what is my function? F of x equals, starting with 1, what do we have?
-1.
Well, x,
Or x
minus
x
1.
minus 1.
There you
Yeah.
go. And what's the rest of them?
X minus 2, x minus 3, and x minus 4.
There you go. That's it. That's all we have to do. And these all have a power of 1, which gives me the minimum degree of 4. Now, since the power is 1, we don't have to write it there. If it was anything greater than 1, we'd want to put it on there. All right. Everybody good with that one? All right. All right. Thumbs. All right. See some thumbs. All right. Good. Cool. All right. Again, let's do it again. All right. For number 3, how many x-intercepts do you see?
2.
2 x-intercepts, roots or x-intercepts, whatever you want to say. All right. B, let's look at our degree. What happens at -2? Does the graph cross or bounce?
Bounce.
It bounced. So that would be a minimum degree of what?
1.
It would be even. So it'd be minimum degree of
2.
2. There you go. And now look at 0. Does it cross or bounce?
Cross.
That would be a minimum degree of
1,
1. And 2
1.
plus 1 gives me
3,
good.
Yeah.
3. Minimum degree there. Okay. Now let's put it together. Look at our x-intercepts. So we have, and that's a 0. So you would have x equals -2 and x equals 0. Now let's put it into factored form. What would I write? F of x equals, what was that?
X minus 2.
Well, if that's a -2, then the sign's going to be opposite, right?
Right.
So it should be x.
Positive 2.
There you go. X plus 2. And then x equal to 0, you just write x. All right. But let's put that x in front. So you'd have x times x plus 2. And since -2, we bounced, what should be the power on x plus 2?
2,
2. There you go.
Okay.
1 and 2.
When you're adding,
Mhm.
when you're adding the degree, or are you counting the like 2, the -2, and the 0?
So the -2 and the 0 are your x-intercepts. So when I'm counting the degree, I'm counting where the graph either crosses or bounces.
Oh.
So since -2 bounced, the minimum degree would be 2. And since 0 crossed, that minimum degree would be 1. Yeah,
I don't know why that's confusing to me, but
it's okay. It's something brand new. Have you ever seen this before?
Nope.
No. See? So that's why
Yeah.
it's something new.
And if it crosses 0, there's an X in front of the parentheses too.
Exactly. So, I mean, if you wanted to, you could put x equals 0 as a factor. It would just be put as x minus 0. But what is x minus 0?
Just X.
X minus 0 is just x.
Too many tricks.
Tricks, yes. All the tricks. Okay, cool. Last one for our polynomials. How many x-intercepts do you see? Or how many roots do you see?
2.
2. 2 roots. All right. Next is all about degree. What is that? Is that a -0.5? Looks like it, right? There's -1, and that would be -0.5. There we go. Okay. So what is the graph doing at -0.5? Crossing or bouncing?
Bouncing.
So the minimum degree would be
2.
2. And what is the graph doing at 3?
Bouncing.
Crossing. And that minimum degree would be
1.
1.
1. There you go. So what is our minimum degree total?
3.
3.
Where am I getting that wrong?
You good?
Can't go wrong with that one. The numbers, okay.
All right. Now, C, we build the polynomial. So that is negative 0.5. So x equals negative 0.5. Or you could even put negative 1/2 like the fraction, whichever. Either one works. And the other one's x equals 3. So how would I put this back in factored form? For negative 0.5, what would I write?
Positive
plus.
point or x plus 0.5.
X plus 0.5. And what would I write for x equals 3?
X minus 3.
That's it. That's it. I mean, we could have it as the other form, like x plus 1/2 times x minus 3, whichever you prefer. Either one works. I'll just box them both. Okay. And that is our polynomial notes. Any questions on that page? Everybody good with it? Good. Seeing some thumbs. All right. All right. Cool. All right. Not bad. Definitely something new if you've never seen it before. So, all right. Okay. Now we are on to rational functions. And rational is just a fancy word for fraction. So, but in a function format. So for this example, it says, fill in the table for the function f of x equals 1/x, then sketch the graph. So here we're going to use an XY chart. So we're going to use Desmos for this. So let me, move this to the side. There we go. And I can, boom. Maybe I can zoom in one more time. Yeah, okay. So what we're going to do is type in that function, and I'm just going to write it as y equals 1/x. And we're going to hit that little gear icon that's on Desmos. And when you hit that gear icon, you're going to pick the convert to table. So we've done this before making XY charts. Okay, and all we're going to do is type in those x values we see on this chart. So 1.1, 0.01, 0.001, 0.0001, and I think you get what's happening here for these values. So when I fill in this table at 1, you get 1, and then we get 10, 100, 1,000, 10,000. What would the next number be?
100,000.
100,000. And what would the next number be?
1 million.
1 million. Good. So every time we add another 0 to that decimal number, the y values get larger. Okay. So now let's see what happens when we make the numbers, the x values, larger towards infinity. So in this case, larger towards 1 million. So we're going to type in these numbers now. Okay. So now I'll have 1, 10, 100, 1,000, 10,000, and we'll stop there because now we see that pattern. So at 1, you get 1 again, and then at 10, 0.1, at 100, 0.01, and then at 1,000, 0.001, and then at 10,000, 0.0001. And what would my decimal number be at 100,000?
Four zeros and a 1.
There you go. 1, 2, 3, 4. There we go. And what would my decimal number be at? 1 million.
5 zeros and a 1.
That's it. 1, 2, 3, 4, 5, and a 1. Okay. Awesome. So there it is. There's our XY chart. And now we are going to use the values we found to answer the following questions. The first question says, according to the table, what happens to the output f of x as the input x gets smaller approaching 0? So it's asking us to look at the first XY chart. So it's saying, as x gets closer and closer to 0, what's happening to your y values? Your y values are doing what?
Increasing.
They're increasing. They're becoming infinitely larger, right? Because if we kept adding the 0 to that decimal place, your next number would be 10 million, and then 100 million, and then you'd get to the billions. So as x gets closer to 0, y starts to get increasingly larger towards infinity. So we can state this as x approaches 0, f of x will approach infinity. So as x gets closer and closer to 0, f of x, or y, starts to get larger and larger and larger towards infinity. So we can also say increasingly larger. Okay. Now look at the other XY chart. And it says, according to the table, what happens to the output f of x as x gets larger and larger towards infinity? So now, as x goes towards infinity, your y values start to approach what number?
0.
0. So as x gets infinitely larger, y now starts to approach 0. So we say, as x approaches infinity, f of x will approach 0. But will it ever touch 0? What do you guys think?
Nope, it's an asymptote.
Oh, you know what an asymptote is. Cool. Yeah, it will never, ever touch 0. It'll get really, really close. You'll have like 0.00000000001, but it's still not touching 0. Okay. Now, since we have Desmos up and we have the XY charts from above, it says to graph the function. So if I move this chart out the way, we have Desmos up and here's our function. So we have the point 1, 1. So this would be 1. And your graph would head up towards infinity and head out to the right. And then if you plugged in -1, as you see over here on the left side of our graph, you would get -1 and your graph would head down towards -infinity as your x values head towards -infinity. Okay. Now, something cool, like you see, if you look at Desmos, it looks like our graph is actually touching 0. But if I zoomed in, you would see that we still are not touching 0. So even if I went to a larger number, I probably have to zoom in more. You see that 66, 68, 69, 70, we are still not touching 0. What if I can't get rid of the table. I could do this though. Let me see, 1 over x. And now it'll actually let me trace. So all the way out there, yeah. Even if you went to that 100, So still going, still going. No matter how far you go down to the x-axis to the right or to the left, our graph will never, ever touch 0. Okay, so everybody good with that page? Oh, I need to fill this in. That would be 0, and that would be infinity. Okay, awesome. All right, which brings us to the definition of asymptote, which somebody just mentioned. So an asymptote is a line that your function approaches and will never touch. Well, it also depends on the type of asymptote you are working with. Here we only have vertical asymptotes, any horizontal, either one. I'll just give a brief description of them. So a vertical asymptote, as in our example says, find those. So for a vertical asymptote, this happens at some value of x. So let's say that x equals c is a vertical asymptote. Then if I were to draw my graph, let's see, make this pretty. There we go. Then at this value of c, let's just put it here, I'm going to have a dashed line. And as my function approaches this vertical asymptote, it will never, ever touch it. It will follow it up to infinity. And if it's coming from the right side, it will follow it down to negative infinity. So something about vertical asymptotes can never, ever be intersected. You can never cross a vertical asymptote. So let's say functions can never cross or intersect. Let's just say never intersect a vertical asymptote. And the reason for that is because vertical asymptotes are part of our domain. And we were finding domain back in 2.1. We don't have 2.1s in functions. So let me double check that. Let's see. So we were graphing functions, and did we find domain? Did we ever mess with domain? I don't remember. We had to somewhere. Linear graphs. I'm not sure if we did. This class. Okay. Well, if we haven't found domains yet, then we're about to today. Okay. So this is the type of asymptote we're dealing with, a vertical asymptote, and it comes from the domain of a rational function. So the domain of a fraction, right? So looking at number 1, let's go ahead and find the vertical asymptote of this function by first finding the domain of the function. And if you think about fractions, what number can you never, ever have in your denominator? You can have negative numbers. There's a specific number that can never, ever be in your denominator.
0.
0. Good. So if we were to find the domain of a rational function, you would take whatever's in the denominator and set it equal to 0. So to find the domain of any rational function, you take the denominator and set it equal to 0. And then you'll solve for x. So if we solve this equation for x, we will get x equals 6. But what happens to this function if I plug in 6?
The denominator is 0.
The denominator will become 0. And if I have 0 in my denominator, the function becomes what? What's that special word?
Undefined.
Undefined.
Say it again?
Undefined.
Oh, undefined. Okay.
Undefined. There you go. So if x is ever 6 for this function, my function will become undefined because I get 0 in the denominator. So what this means is that for this function's domain, we can be any number we want except for which one?
6.
6. So when we state the domain of our function, we're going to say x cannot equal 6. So there's our domain. X cannot equal 6. Okay, well, the best part of this is that the domain of a rational function and a vertical asymptote go hand in hand. If you have the domain of a function, then you have of a rational function, then you have your vertical asymptote. So if our domain is x cannot equal 6, this means that my vertical asymptote is x equals 6. Okay. And it would only be right to show you what that actually looks like. So let's look at Desmos again. Let's plug this function in so you see what an actual vertical asymptote is. So let me type this function in. 2x squared plus 7 over x minus 6. And I might have to zoom back over here. Oh yeah, I went too far. There we go. All right, so look how crazy this function looks. But now, if I type in this line, x equals 6, look what's going on here. Your graph seems to be getting really close to that line, but will it ever touch it? What do you guys think? Will we ever touch that red line, x equals 6?
No.
Nope.
No,
No.
no. And just by my lovely sketch that I drew over here, just like I said, one tail of the graph will head towards positive infinity, and another tail of the graph will head towards negative infinity. So this graph will never, ever touch x equals 6. It will get really close, but it will never touch. So just had to give you more visual representation of what we're working with. Okay. All right. So now, to keep things really simple, all we're looking for are vertical asymptotes of these functions. So let's find their domain. If you have the domain, you have the vertical asymptote. So for number 2, let's find that domain. And that means you will take the denominator, x squared minus 6x minus 16, set it equal to 0. And now we have a quadratic equation. And these quadratic equations are the easiest ones to factor because all we need to worry about are the factors of the constant that will make the middle number. And also look at your signs. If that's minus minus, you're going to get x plus a number, x minus a number equal to 0. What are 2 factors of 16 that can make 6?
8 and 2.
8 and 2. Who's going to be positive? Who's going to be negative?
The 8's going to be positive. Wait, is it backwards? No, and the 2's negative.
You were good on second guessing. The 8
Oh,
will
I'm
be.
sorry, it was backwards.
You're good. You're good. The 8 will be negative, and the 2 will be positive because we needed to get us to negative 6, right? Because if we wrote this out, you'd have negative 8 plus 2, which gave me negative 6. Okay, there you go. It's factored. And now set these equal to 0. And what values of x do we get?
-2 and +8.
-2 and +8. X equals -2, x equals +8. But what happens to the denominator if x is -2 and or if x is 8. The denominator will become,
0.
and can we
So are
have
there
that?
there's 2 asymptotes?
Good. We have 2 asymptotes. You can have multiple asymptotes. So you can have more than one. So x can equal -2, x can equal 8. That is your domain, meaning if you have your domain, you have your vertical asymptotes. X equals -2 and x equals 8. That's it. Okay. Everybody go with that one. All right. So doing the same thing for the others, 3 and 4. Okay. 3. Fine. Oops. Wanted to be green. There we go. Find our domain. Set your denominator equal to 0. And x squared minus 4, what is that factor to?
X plus 2, x minus 2,
Good, because it's a difference of
2 squares.
squares. Very good. And then solve for x. You'll get x equals -2, x equals 2. But again, if x is -2 or 2, the denominator becomes 0. So there's our domain. And if you have your domain, you have your vertical asymptotes. X equals -2, x equals 2. All right, last one for these. There we are. Take your domain, find your domain, and take your denominator, set it equal to 0, and 8x minus x squared. All right, so these are the ones where we factor out a greatest common factor. So what could we factor from 8x and -x squared?
X.
An x. So if we factor out an x, that'll leave me with 8 minus x equal to 0. Now, set both of these equal to 0, and what are my 2 answers?
X equals -8.
X equals, well, if that's 8 minus x, then it's going to be x equals
+X.
+8 or +x, just like you said. So 8 equals +x or x equals 8. And what about this x? That'll be x equals
0.
0. There you go. X equals 0. So there's our domain. We cannot equal 0 or 8. And my vertical asymptotes are x equals 0 and x equals 8. There you go. That is how you find vertical asymptotes. If you find the domain of a rational function, you have the vertical asymptotes for that function.
So you really don't do anything with the top.
No, we do not. The top will help us find something called horizontal asymptotes.
Don't go there. You'll confuse me.
But I don't think we do that in this lesson. No. So, yeah, it's all about vertical asymptotes here.
Cool.
Okay. Awesome. Okay. So next, write the equation of a rational function that satisfies the following requirements. So 5 says we will have a vertical asymptote at x equals 10. So this is just like what we were doing earlier today. We were reversing everything. We were reverse engineering. So it's giving us a vertical asymptote at 10. So what if I wrote this as a rational function? What would my denominator be? And remember, when I say work backwards, they're giving us these, which means we work backwards to this, and create a rational function such as that. So everything backwards, backwards, backwards. So if they're giving us a vertical asymptote at x equals 10, what would my denominator be?
0.01.
X minus 10.
To do it.
X minus 10.
Oh,
And then it says create any type of rational function. So what do you want to put in the numerator? Anything you want. Just say a number.
X plus 5.
There you go. Boom. We have created a rational function that would represent this vertical asymptote. That's it. That's all we had to do. So the numerator can be anything because all we're worried about is the denominator. Okay, let's do it again. They are giving us vertical asymptotes at x equals -5 and x equals -2, x equals +2. What would my denominator look like?
X equals 5?
Well,
X plus 5 and X minus 2.
there you go.
Yeah.
There you go. And whatever we want in the numerator. How about just x? Doesn't matter, right? Okay. And then
I have a question.
what's up?
Okay, so you know how if X goes through 0, it's like outside of the parentheses.
Mhm.
So if it bounces on 0, would it be like X squared out of the parentheses? Is that how that works?
Very good. Yes.
Okay.
Yeah.
And then can it have like a coefficient with it, like a 2x or no? Or like a number with it?
It could if we were solving for coefficients.
Oh, okay.
Yeah, but
Cool.
that's not something we do in, I think, for these lectures. But yes, you could solve for a coefficient if you had to.
Okay. And it
Yeah.
can't be like a -x outside of the parentheses, right? It's only
You can have
positive.
you can have a -x. It just depends
Oh.
on the function. Yeah.
Okay. So if it's going down, it'd be a -x, but if it's going up, then it'd be a positive.
Yes.
Cool.
Yeah.
Okay, cool. Funky. I was just asking.
All right. Okay. 7. You have the domain equals x cannot equal plus or minus 5. So basically, they're giving us, I mean, they're already giving us those steps. So they're saying x equals -5 and x equals +5. So what would the denominator of my rational function look like?
X plus 5 and X minus 5.
Good. X plus 5, x minus 5. And what do you want to put in the numerator?
2X plus 1.
Oh, great. There you go. So we were just constructing a rational function whose denominator would represent those vertical asymptotes. Okay. Awesome. So everybody good with that page? All right. Thumb. All right. Cool. Yep. Next. All right. Applications with rational functions. So heavy metal contaminants in a cement quarry may be removed from the soil by planting sunflowers. Use the following model to estimate the number of sunflowers in thousands needed to remove P% of the contamination. Note that P is a percent, so 25% means P equals 25. Okay. So they're giving us the rational function S of P equals 90 over 100 minus P. And for A, it says, how many sunflowers would it take to remove 50% of the contamination? So what would we plug in for P on this one?
50.
50. Good. So we would have S of 50 equal to 90 over 100 minus 50, which would give me 90 over 50, which would reduce to 9/5. And let's see, we are using the model to estimate the number of sunflowers in the thousands. So what is 9 divided by 5?
1.8.
1.8. But now we would multiply that by what?
1,000?
1,000, right? We'd multiply that by 1,000, and that's going to tell us how many sunflowers we're able to get rid of, or we're able to plant, sorry, we're able to plant to get rid of that pollution or contamination. So 1,800, right?
Yeah.
So we need 1,800 sunflowers to remove 50% of the contamination. Okay. Then how many sunflowers would it take to remove 99%? So we are going to plug in 99. And you would have 90 over 100 minus 99. And that would give you 90 over 1. So that would give us 90. But then multiply that by 1,000. And what would that be?
90,000.
90,000 sunflowers. So you need 90,000 sunflowers to get rid of 99% of the contamination. Okay. Now, C, what percent removal cannot be achieved? What do you guys think? What percent of contamination could we not get rid of?
100?
100%. And why is that? What would happen if we plugged 100 into this function?
The
would cross over the
denominator would be
asymptote?
0.
We would not cross over the asymptote, but
The denominator would be 0.
the denominator would be 0, which would give us undefined. So this means that you can't cross the asymptote because your asymptote would be at 100. So we would never able to be touch that asymptote. So we would never be able to get rid of 100% of the contamination. Think about it. Your can of Lysol says how much bacteria does it kill?
99.9.
99.9%. If they state 100%, they're getting sued, right?
Yep.
So it's just not possible to get rid of 100% of the contamination. Okay. So everybody good with that? All right. All right, another one. 9. It costs money to keep our lake at NVC clean. That lake is green. I don't know about that. Say there are 2 tons of pollution in the lake, and the cost C in hundreds of dollars of removing X tons of pollution is C of X equals 70x over 2 minus x. How much would it cost to remove half a ton of pollution? All right. So if x represents tons of pollution, and we want to remove half a ton of pollution, what number would we plug in for x? What number represents a half?
0.5.
0.5. So you would have C of 0.5, and you would have 70 times 0.5 over 2 minus 0.5. And 70 times 0.5 gives me 35 over 2 minus 0.5 gives me 1.5. And what is 35 over 1.5?
$23.3333.
23.33 repeating. But remember, that price is in the hundreds. So what would we multiply 23.33 by?
100.
100. So how much would it cost to remove half a ton of pollution?
I don't know. 23.3. I don't know where you cut it off at.
Yeah, well, if you're thinking of money, can you pay somebody in repeating decimals?
No.
No, right? So to remove half a ton of
300.
pollution, it would cost $2,333.33. Okay. And what would happen if we try to remove all 2 tons of pollution? Well, what would you plug in for x?
It'll be undefined.
It'd be undefined. So C of 2 would be 70 times 2 over 2 minus 2. You'd get 140 over 0. Yes, it's undefined, but in terms of money, if you try to remove all 2 tons of pollution, we would be spending how much money? So if it costs $2,333 to remove half a ton, how much more would it cost to remove 2 tons?
So it just
Four times that much.
Well, you can say 4 times a lot. How about we just say it would cost a lot more? That's it. So what would happen if MVC attempts to remove all tons of pollution? NVC would go broke. How's that sound? The money would just exponentially increase. So we wouldn't have all the money in the world to remove 2 tons of pollution in that lake. All right. Okay, guys, last one. We made it. 10. A typical round of golf is 18 holes, where your cumulative score for the round is the sum of all shots you took on each hole. For example, if you took 4 shots on each hole, your score is 4 times 18 equals 72. So describe the relationship between the rounds of play and the score on 18 holes, and which scores are impossible and why. All right, so looking at the graph, the y-axis represents the rounds of play in your whole lifetime. So if you play golf a lot, it's over the rounds over the years you've played golf, and the score you have made on these rounds. So looking at this graph, well, we see, we can answer B already. What is an impossible score on 18 holes, guys?
Zero?
You could get 0 by not playing. So think about golf. There's 18 holes. Is it possible to score an 18? If you score an 18, this means you got a what on every single hole?
A hole in
Hole in
one.
A
one?
hole in one. Is it possible for somebody to make a hole in one on 18 holes?
Probably not.
Maybe.
No, it is not possible. I don't think it's ever been done, right? So B, you cannot score an 18. You will never score an 18, right? Okay, but looking at the graph, so we're going to read this graph from right to left. So look at this. Let's say we first started out at golf. We have played 10 rounds of golf. And on 10 rounds of golf, we're making scores that are close to 90 and above. And then we get more experience. Let's see, 10, 20, 30, 40. We play 50 rounds of golf. We're now experts. And now we're making scores close to whatever this is, between 18 and 36. So let's say that is, what's it go by? 18, 18, so 9. So that would be 27. So now you have played 50 rounds of golf, and an average of these scores, you are now making a 27 on every time you play, which is phenomenal, right? And then let's say you played, 60, 70, 80. Let's say you played 80 rounds of golf. You are now getting really, really, really close to 18. So all we're trying to say here is, what is the relationship? The more rounds, the more experience you have with golf, what's going to happen with your score?
It's gonna get better.
It's going to get better. That's it. That's all we want. So for A, the more rounds, the better score. That's it. No, that's not going to happen for me ever. Not even in disc golf. Terrible at both. Okay. And that's it, guys. That is rational functions and polynomials. I am mathed out. Good thing it's Wednesday, right? All right. Well, that's it. If you got questions, stick around. If not, see you on Monday.
Our homework